Imagine you need to solve a math problem, and you have two options, a 100-page notebook or a 500-page notebook. Both will get the job done, but the 100-page notebook is far more efficient with physical paper. In algorithms, efficiency has two fronts, time and space. Space complexity is the total memory required. It splits into a fixed part and a variable part. Total memory is the constant memory added to the variable memory. The fixed part never changes. Declaring 3 simple integers allocates exactly 3 locked memory blocks. The variable part, however, scales dynamically with your input, n. An array of size n demands only a handful of locations for small inputs, but thousands for massive ones. Understanding how this variable memory scales determines whether your code runs flawlessly on everyday hardware or crashes an entire system by exhausting available RAM. To accurately track that memory, we separate the raw data you feed into the algorithm from the extra scratchpad memory the algorithm needs to do its calculations. That extra scratchpad is called auxiliary space. Total space combines input space and auxiliary space. Let's look at a loop summing elements of a given array. The array is the input. To calculate the sum, the program only needs 2 extra variables, one to track the running total and one for the loop indexed. Because those variables remain constant regardless of array size, the auxiliary space is fixed at O of 1. Consider an algorithm built to copy one array into another. The first array is our input, but to execute the copy correctly, we have to generate an entirely new array of the exact same size. So our extra scratchpad memory grows directly alongside the input, resulting in a linear auxiliary space of O of n. Pause the video here. Look at the code on screen and identify the input data, find the extra variables declared, and calculate the auxiliary space on your own before moving forward. When we introduce two-dimensional structures like an n by n matrix, the memory requirement balloons geometrically. Instead of a single row of n elements, the system allocates n rows of n elements, pushing the space complexity to a massive O of n squared. When calculating the final total space, we drop constant multipliers. An algorithm using 2 arrays of size n technically uses 2n memory blocks, but we express that simply as O of n. We analyze the trajectory of the memory growth, not the literal byte count. Code without any visible array declarations can still consume massive amounts of memory. Recursive functions are a prime example of this trap. When a function calls itself, the system allocates a temporary memory frame in a physical stack. If function 4 calls function 3, and 3 calls 2, each step forces yet another block of memory onto that stack until it finally hits the base case of 0. To evaluate the final space complexity, we measure the maximum height of this recursive stack. A maximum depth of n frames dictates that the recursion operates in O of n space. Algorithms routinely hide these memory requirements deep in the system architecture. A deeply recursive function is a severe liability in environments with strict memory constraints. Designing an effective algorithm is a continuous balancing act between maximizing execution speed and surviving within the bounds of system memory. This graph illustrates how these memory bounds are tested. A constant O of 1 space requirement stays completely flat. A linear O of n space grows steadily in proportion to the input, but a quadratic O of n squared curve arcs aggressively upward, draining resources rapidly. For exam review, lock in these 3 definitions. Space complexity is the total memory required during execution. Auxiliary space is the extra working memory excluding the input, and total space requirement is the sum of both the input and the